Hi Professor and TAs. Today our project is FPGA-based fast Fourier transform accelerator for voice optimizer. Our group includes Bolong, Rui, Clora, and Jiacheng. First, we are implementing a voice noise cancelling module using FPGA. First, this module can reduce the audio sample noise using the fast Fourier transform to convert the input audio from time domain to the frequency domain. And in the frequency domain, we are applying some high frequency noise filters to filter the useless information and other noises. And then we apply the inverse FFT to convert the data back from the frequency domain to the time domain. We are using FPGA because the fast Fourier transform algorithm has intensive computation workload. So we are using FPGA for its parallel computing and high throughput ability. Finally, we are achieving that 18 times faster than the ARM CPU platform and 7.5 faster than x86 platform. This is our structure of our project. First, we have an audio sample and convert it into array, and we feed the array into the FPGA, and then FPGA will output the array, and then we convert it back, and we can get the noise cancelled audio sample. And this is the fast Fourier transform algorithm. You can see that it converts the audio from time domain to the frequency domain based on different frequencies, because in the different frequency can reveal more details about the signal. In the frequency domain, we have a real part, the imaginary part. For these two parts, we are applying the filters that we can eliminate that useless information, and then we can do the inverse fast Fourier transform. This is the butterfly convolutional multiplication. You can see that fast Fourier transform algorithm divided the audio sample in pieces and combined pieces in pair to do the convolutional multiplication to convert it based on the different frequency characteristic. And then this is the audio processing part.
After the fast Fourier transfer process, we got the spectrum of the input audio data. To do the noise filtering, we implement a bandpass filter and a threshold filter to remove most of the unwanted frequency components. The bandpass filter keeps valid components between 20 to 2400 Hz, and the threshold filter removes the points whose amplitude spectrum is less than 1. Then we do a gradient spectrum attenuation to further reduce the effects of noise by multiplying specific factor on different ranges of components. Besides, we also calculate the amplitude spectrum and find the base frequency.
And the next part is the problems and the key optimization. So the first challenge we face is the DSP resources usage. Initially, when we analyzing the resources usage report, we found that our design was exceeding the limits of DSP resources. So after further investigation, we found out that they were being consumed primarily for computing sine and cosine values. And to address these challenges, we explored alternative approaches to implement a lookup table for sine and cosine values. This approach allows us to use pre-computed sine and cosine values from these tables, and this so that we can significantly reducing the DSP resources from 102% to 32%.
As the variable type of our input and output is float, and the FIFO port between ARM and FPGA only supports 32-bit int, therefore we bring in a union type to convert it to int before sending it to the FPGA. And on the FPGA side, we did the reverse thing to convert it back and then do the computation. When the FPGA sends the output result back to ARM, it follows similar steps. Here is an example about how we use union type for conversion.
The FFT algorithm mainly contains 3 for loops. As you can see, the butterfly loop and the DFT loop are unbounded, which is caused by the variable declared at the beginning of the stage loop. So we decided to get rid of the stage loop and creating multiple copies of the butterfly loop and DFT loop. After that, we force the DFT loop have a constant bound by adding one more if statement inside the loop. After that, we use the HLS directive to fully pipeline the DFT loop and unroll the butterfly loop. The reverse base and bit reverse functions are two critical components of the FFT algorithm. To enhance the algorithm efficiency, we have also pipelined these two functions.
So the next section is the evaluation. In our HLS hardware simulation report, we achieve a significant drop in cycles, reducing over 2 million cycles time. However, because FFT is one of the hardest applications to route on FPGA, routing becomes less feasible when resource utilization exceeds 50%. And because of that, our FPGA optimized design saw a significant reduction of about 732,000 cycles. Furthermore, we achieve almost 18 times latency speedup compared to the ARM CPU. When comparing the baseline with the optimized FPGA latency, we note that despite a reduction of over 20 cycles in execution time, a portion is still consumed by communication due to processing over 32,000 data points. Regarding hardware uses, because of the feasible routing issues, we have utilized most of our hardware resources to optimize our project. For instance, our lookup table has already reached 33% utilization in our efforts to optimize latency. So, overall, these accomplishments are particularly remarkable given the challenges we faced, such as processing over 32,000 input data points and executing 14 stages of FFTs.
Here there is a demo video to show how our project works.
Hi, I'm Jia Zhengzhu. I will quickly show you how to run our demo. After loading bitstream on FPGA, we run command make FPGA to generate our output. We can see that the output field contains real part and imaginary part of the processed audio data. Then we use the Python script to convert the output data back to audio. And this is our input audio. And this is our output audio. Now we can compare their difference. We can see that most of the noise have been filtered. Thank you.